Hey everyone, and welcome to The Explainer. Today, we're jumping into a real classic from the coding interview circuit, the missing number problem. This one is fantastic, and here's why. It's got a bunch of different solutions, and each one gets a little more elegant, a little more clever than the one before. All right, let's get right into it. So imagine this gets dropped in your lap during an interview. You're handed an array. Now, we know two things for sure about this array. It has n unique numbers in it, and every single one of those numbers was pulled from the complete set of 0, 1, 2, all the way up to n. So a perfect sequence is supposed to be there, but it's not. Exactly one number is gone. Your job? Find that missing number. Okay, let's make this crystal clear with an example. Say your input is the array you see here, 3, 0, 1. Right away, you can see there are three numbers. That means n is 3. So the full complete range of numbers we should have is 0, 1, 2, and 3. Now just look at the input we were given. Which one's not there? Yep, it's 2. And that's exactly what our algorithm needs to figure out and return. So where do you even start with a problem like this? Well, the first place most of our minds go is down a very logical, very intuitive path. You can think of this as our baseline approach, the brute force way to get it done. It might not be the fanciest solution in the box, but you know what? It works.
The thinking here is pretty simple, right? If all the numbers were in perfect order, the missing one would stick out like a sore thumb. It would create an obvious gap. So the plan becomes, let's just put them in order first. If we sort the array, we should see the number 0 at index 0, the number 1 at index 1, and so on. The very first spot where that pattern breaks, well, that's where our missing number is hiding. So let's actually walk through this. First, we sort the array. Our 3, 0, 1 becomes 0, 1, 3. Now, after we handle a couple of edge cases, like what if 0 is missing, we just loop through it, comparing the value to its index. Is the value at index 0 the number 0? Yep. How about index 1? Is the value 1? Yep. But then we get to index 2. We expect to see the number 2 there, but instead we find a 3. That mismatch tells us everything we need to know. The missing number must be 2.
And the heart of this whole method really boils down to this simple loop. At every single step, we're just asking one question. Is the value, nums of I, different from its own index, I? The very first time the answer is yes, we found our gap. We can immediately return that index I, because that's the number that was supposed to be in that spot. Boom. Problem solved. Okay, so the sorting approach works. It gets the right answer. But can we do better? This brings us to a classic idea in computer science, the space for time trade-off. What if we were willing to use a little more memory to, buy ourselves some speed? This leads us straight to our second approach, the hashing method. The big idea here is to create a kind of checklist. Just imagine you have a piece of paper with all the numbers that should be there, from 0 all the way to n. Then you just go through the input array you are given, and for every number you see, you just put a check mark next to it on your list. When you're all done, what's left? You just scan your list for the one number that never got a check mark.
So how do we actually build this checklist in our code? Well, first we create a brand new array. Let's call it our scene array. It's going to have a spot for every number from 0 to n. Then we loop through our original input numbers. For each number we find, let's say we see the number 3, we go to index 3 in our new scene array and we mark it. After we've done that for every single number in the input, we just do one final quick loop through our scene array to find the one spot that was never touched. That index is our missing number.
And this is basically what that looks like in practice. Here, a new array called v is made, and it's filled up with -1 to start. That's just a placeholder for unseen. The first loop zips through our input nums, and for each number, it places that number at its own index in v. So v at index 3 would get the value 3, v at index 1 gets 1, and so on. The second loop then just scans v looking for the first spot that's still a -1. That's our guy. That index is the answer. Dead simple, right? All right, now we get to the really, really fun part. The next two solutions are where you level up. You go from just solving the problem to solving it with a bit of style, a bit of elegance.
These are those aha moment solutions that are built on some seriously cool mathematical properties. This is the stuff that really shows you have a deep understanding of what's going on. Okay, check these out. On the left, we've got a solution using a famous formula from the mathematician Gauss. The logic is just beautiful. We know what the sum of a perfect sequence from 0 to n should be. We can calculate that in a snap. Then we just add up the numbers we actually have. The difference between the sum we expected and the sum we got, well, that has to be the missing number. Then on the right, we have an even more clever trick using the bitwise XOR operator. The magic of XOR is that any number XORed with itself equals 0. So if we XOR everything that should be there with everything that is there, all the matching pairs just cancel each other out. They just vanish, leaving behind only the one number that didn't have a partner, our missing number. Now let's look at the code for that summation trick. It is so clean and so concise. That first line, that's just Gauss's formula. It instantly calculates the theoretical perfect sum of all the numbers from 0 to n. The next line just adds up what we actually have in our input array. And that last line? Just simple subtraction. Expected sum minus actual sum, and you've got your answer. How cool is that? And now for the XR wizardry. We start with a variable, let's call it ands. First, we loop from 0 to n, and XR ends with every number that should be in the sequence. Then, we do it again, but this time we XR it with every number that's actually in our input array. And because any number XORed with itself becomes 0, every number that's present in both sets effectively cancels itself out. The only value left standing at the end, the only one that survives, is the one that never found its pair, our missing number. It's incredibly efficient. So we've got 4 different ways to solve the exact same problem. Now, in a real coding interview, this is where the rubber meets the road. It's not just about finding an answer. It's about understanding which answer is the best one for the job and being able to explain why. So let's put them all head to head. And this table right here, this tells the whole story. Let's look at time complexity. That's basically how much does this slow down as our input array gets huge. You can see sorting is the slowest at n log n. The other 3 are all linear, or O of n, which is a massive improvement. But then you have to look at space complexity. How much extra memory does it need? The hashing method is fast, but it pays for that speed by using a whole extra array's worth of memory, O of n space. And this is where the summation and XR solutions truly shine. They give us that top-tier O of n speed while using basically no extra memory. That's what O of 1 means. That combination makes them the gold standard solutions for this problem. So, what's the big picture here? What should we take away from this? First, always be thinking about that trade-off between time and space. Second, sorting is a fantastic tool, and it's a great first instinct, but don't stop there. It's often just a stepping stone to a better solution. Third, and this is a huge one, always keep your eyes peeled for hidden mathematical properties or patterns. They're often the key to unlocking those super elegant and efficient solutions. And finally, remember that best isn't always a one-size-fits-all answer. It can depend on the specific rules of the game. If memory was insanely tight, that hashing method would be off the table. And that brings us to our final thought for today. Picture it. You're in the hot seat in an interview. You know all 4 of these solutions. Which one do you bring up first? Do you start with the simple sorting method, just to show you can get a solid, working solution on the board and then improve from there? Or do you jump straight to the optimal XOR or summation approach to really show off your problem-solving chops? The path you choose actually says a lot about how you think. Thanks for joining this explainer.